What is the main motivation behind the development of Gecko embedding model?
The main motivation behind the development of the Gecko embedding model is to leverage the vast world knowledge of large language models, LLMs, to improve text embedding models. The goal is to create a highly versatile and efficient embedding model that can benefit from the comprehensive knowledge stored in LLMs. By using insights from knowledge distillation, the Gecko model is designed to generate a two-step LLM-powered embedding model. This approach aims to enhance the quality of text embeddings by utilizing LLMs to generate relevant tasks and queries for passages, re-rank passages, and obtain positive and negative passages based on LLM scores. The key focus is on improving text embedding models by directly leveraging the power of LLMs, rather than solely relying on human-labeled data or domain-specific performance. The development of Gecko seeks to address the challenge of creating a single embedding model that can support multiple tasks efficiently and effectively by harnessing the extensive knowledge and few-shot learning capabilities of LLMs.
How does Gecko leverage insights from knowledge distillation in its approach?
Gecko leverages insights from knowledge distillation in its approach by using a two-step LLM-powered embedding model. Firstly, it uses a few-shot prompted LLM to generate relevant tasks and queries for each passage. Then, it embeds the concatenated task and query using a pre-trained embedding model to obtain nearest neighbor passages. Subsequently, Gecko uses the LLM to re-rank the passages based on their relevance to the query, obtaining positive and negative passages based on the LLM scores. This re-ranking step is crucial as it enhances the quality of the model by discovering that the best passage to answer the generated query often differs from the original source passage. By incorporating knowledge distillation techniques, Gecko effectively integrates the vast world knowledge of LLMs into its text embedding model, leading to improved performance on tasks such as document retrieval, sentence similarity, classification, and clustering.
What is the significance of the re-ranking step in Gecko model?
The re-ranking step in the Gecko model is significant because it enhances the quality of the text embeddings by leveraging the vast world knowledge of large language models, LLMs. This step involves using an LLM to re-rank the nearest neighbor passages obtained from a pre-trained embedding model based on their relevance to the generated query. The re-ranking process is crucial because it helps to identify the best passage to answer the generated query, which may differ from the original source passage. By re-ranking the passages, the Gecko model ensures that the most relevant and informative passages are selected as positive examples, leading to improved performance in text embedding tasks. The re-ranking step plays a key role in refining the quality of the embeddings by incorporating the global preferences and domain knowledge of LLMs, ultimately contributing to the model's success in achieving state-of-the-art performance on benchmarks like MTEB.
How does Gecko use large language models, LLMs, to generate relevant tasks and queries for text embedding?
Gecko uses large language models, LLMs, to generate relevant tasks and queries for text embedding by leveraging insights from knowledge distillation to create a two-step LLM-powered embedding model. Firstly, starting with a large corpus of in-labeled passages, a few-shot prompted LLM is used to generate a relevant task and query for each passage. The LLM is instructed to read a sampled web passage and generate both the task description and a relevant query for the task. The task description describes the type of retrieval, such as question answering or fact-checking, while the query aligns with the task. Secondly, the concatenated task and query are embedded using a pre-trained embedding model to obtain nearest neighbor passages. An LLM is then used to re-rank these passages based on their relevance to the query. This re-ranking step is crucial as it enhances the quality by identifying that the best passage to answer the generated query may differ from the original source passage. By combining the LLM-generated and LLM-ranked data with human-annotated data, Gecko achieves the best performance on the MTEB benchmark among models with compatible embedding dimensions and model sizes, showcasing the effectiveness of using LLMs to generate relevant tasks and queries for text embedding.
What is the role of FRET dataset in training the Gecko model?
The FRET dataset plays a crucial role in training the Gecko model by providing diverse and high-quality synthetic data for fine-tuning the text embedding model. The FRET dataset is generated through a two-step distillation process using large language models, LLMs. Firstly, LLMs are used to generate relevant tasks and queries for passages from a large web corpus. These tasks and queries cover a wide range of topics and linguistic patterns, ensuring the diversity of the dataset. Secondly, LLMs are employed to mine positive and hard negative passages for each generated query, ensuring that the model is exposed to relevant and challenging examples during training. The FRET dataset consists of 6 million examples, each containing a task, a query, a positive passage, and a negative passage, which are used in combination with other academic datasets for fine-tuning the Gecko model. By leveraging the FRET dataset, Gecko achieves superior performance on the Massive Text Embedding Benchmark, MTEB, and demonstrates strong generalizability across various tasks, showcasing the effectiveness of using LLM-generated data in training versatile and high-performing text embedding models like Gecko.
How does Gecko perform on the MTEB benchmark compared to other models with different embedding dimensions and model sizes?
Gecko performs exceptionally well on the MTEB benchmark compared to other models with different embedding dimensions and model sizes. Specifically, Gecko-1b, with 768 dimensional embeddings, achieves the best performance on the MTEB benchmark among models with compatible embedding dimensions and model sizes. It often outperforms other systems that use either larger base models, 7b, or higher dimensional embeddings, 1K to 4K, even when trained solely on the LLM-generated FRET dataset, making MTEB a pure zero-shot benchmark. Gecko shows strong performance compared to other baselines. This demonstrates the effectiveness and efficiency of Gecko in text embedding tasks, showcasing its superiority in balancing retrieval and semantic textual similarity (STS) performance, and setting a new state-of-the-art on classification, STS, and summarization tasks. Gecko's performance highlights its versatility and effectiveness in handling diverse tasks and domains, making it a highly competitive model on the MTEB benchmark.
Explain the process of LLM-based positive and negative mining in Gecko model.
In the Gecko model, the process of LLM-based positive and negative mining involves leveraging large language models, LLMs, to identify relevant positive passages and hard negative passages for a generated query. First, an existing embedding model is used to retrieve the top neighbors from the corpus based on a generated query. Then, the same LLM used for query generation is employed to rank these retrieved passages according to their relevance to the query. Two few-shot prompted LLM ranking functions are utilized: query likelihood and relevance classification. The query likelihood function measures the log likelihood of a generated query given a passage, while the relevance classification function measures the log likelihood of a specific relevance label given the query and passage. These rankings from the two prompting methods are then ensembled using reciprocal rank fusion, RRF, to create a final ranking function. This process ensures that the model considers a wide range of passages and selects the most relevant positive passage and hard negative for each generated query. The LLM scores are used to index the passages and select the new positive target, which may differ from the original seed passage, providing a more globally preferred passage for the query. Additionally, the LLM scores can also be used to select hard negative passages, either by choosing the lowest scoring negative or sampling from the remaining nearest neighbors. This comprehensive approach results in the creation of the FRET dataset, consisting of 6 million examples, each containing a task, a query, a positive passage, and a negative passage, enhancing the quality and diversity of the training data for the text embedding model.
What is the training recipe for Gecko model, including the pre-fine-tuning and fine-tuning stages?
The training recipe for the Gecko model involves two main stages: pre-fine-tuning and fine-tuning. In the pre-fine-tuning stage, a large text corpus is used for self-supervised tasks to expose the model to textual diversity. This stage includes adding a dataset-specific task feature before each query, such as question answering or search result, to inform the model about the task being optimized. The contrastive learning objective is optimized with in-batch negatives, using cosine similarity as the similarity function. Hard negatives are not utilized during pre-fine-tuning, and the maximum batch size that fits into the device is used. For fine-tuning, a novel fine-tuning dataset called FRET, Few-Shot Prompted Retrieval Dataset, is created via a two-step LLM distillation process to identify positive and hard negative passages for each generated query. The FRET dataset is combined with other academic datasets in a similar format, each containing a task description, input query, positive passage, and negative passage. The fine-tuning stage optimizes the in-batch cross-entropy loss, where the query should distinguish the positive target from the hard negative, other passages in the batch, and other queries in the batch. The model also uses same tower negatives to help with symmetric text embedding tasks. Additionally, the model incorporates the MRL loss to support multiple dimensions of embeddings with a single model.
How does Gecko incorporate academic training datasets in its unified fine-tuning mixture?
Gecko incorporates academic training datasets in its unified fine-tuning mixture by combining the FRET dataset, which is generated using LLMs, with other academic datasets formatted in a similar way. These academic datasets include natural questions, Hotpot QA, Fever, Med MCQA, SNLI, MNLI, and several classification datasets from Hugging Face. Additionally, for the multilingual model, training sets from MIRACL are added. All these datasets are pre-processed to have a unified encoding format consisting of a task description, a query, a positive passage, and a negative passage. By combining FRET with these academic datasets in the same format, Gecko creates a novel fine-tuning mixture. This mixture is then used to train the embedding model, Gecko, using a standard loss function, optimizing the model for a diverse set of downstream tasks across different domains and skills.
What is the significance of using classification data for contrastive learning in Gecko model?
The significance of using classification data for contrastive learning in the Gecko model lies in its ability to seamlessly incorporate classification training sets into the contrastive learning objective without compromising performance on other tasks. By pairing each input text with another input, sharing the same label as a positive target, and selecting a hard negative input with a different label, the model can effectively learn to distinguish between positive and negative examples within the same batch. This approach ensures that the model focuses on differentiating between positive and negative examples, improving its ability to understand semantic similarity and classification tasks. Additionally, assigning unique IDs to each triple of inputs helps the model easily distinguish between in-batch negatives, preventing false negatives and enhancing the learning process. Overall, incorporating classification data in contrastive learning enhances the model's performance on classification tasks while maintaining its effectiveness on other text embedding tasks, contributing to the overall versatility and efficiency of the Gecko model.